Okay. All right, so today I get the pleasure of introducing myself. My name is Gary DeBoer, and I'm going to tell you a little bit about some chemistry that I've done in previous years with the Air Force Research Lab. Okay? And that's kind of an exciting thing lately. I'll talk about the U.S. Space Force, and you've heard some of that, so I'll maybe talk about some of that as well. So I spent a number of summers over at the Air Force Research Lab when it was at the Hanscom Air Force Base, which is way out there near Boston. So a long ways to go to get out there, but it's out there. And it's a very nice looking place. It's kind of like a college campus, except you got to go through a gate to get in there. But once you're in there, there's these green fields and parks and stuff. And a lot of the parks have these airplanes mounted up on them, right? With flags flying, things like that. So a pleasant place to be. Boston is in the summers, far away from the heat of Texas. Yeah. So that's nice. Here's a view of Boston, right? There you go. Pretty sight, isn't it? Okay. All right. So nice place to be. So this is sort of the outline of what I plan to talk to you about today. I usually tell my students to take the IMRAD approach: introduction, methods, results, and discussion. Right? IMRAD approach. You can't go wrong with the IMRAD approach. Right? I'm going to modify it a little bit and do the IMRADI approach here, where I put the introduction at the end. Okay? Because you're probably more interested in that kind of stuff. And if I talked about that first, you wouldn't pay any attention to anything else. So I'm going to try it this way. All right. So we're going to tell a little bit about the methods of research we did at the Air Force Research Labs, some of the results, discuss the results a little bit, and then have a little discussion at the end over there. All right. So this is what we're interested in. The Air Force has airplanes and a lot of space assets, as we call them. And the chemistry is different down here in the troposphere where we live versus up there in the stratosphere and the thermosphere where these assets are. Okay. So down here we breathe in oxygen. But we should be more specific there. We breathe in oxygen molecule, O2, the diatomic molecule. Yes? And that's good. Yes? Up there, where less of the short wavelength light is filtered out, O2 is blown apart, and it's mostly O atom. Okay? And you can see the density of the O atom increases here, okay, as you get to higher altitudes. So our high-flying airplanes and space vehicles, their atmosphere is dominated by oxygen atoms. Okay? And oxygen atom is a di-radical. And if you think about radicals, maybe your grandparents, stuff like that, of that generation, you think of them multiplied by 2. Right? Okay, so what we want to do is do the chemistry, right, without having to go up there, right? We want to do it in a lab, okay, with a little bit more control. So we want to be able to produce O atoms, yes, and have those O atoms react with other stuff, the spacecraft itself, or maybe the effluents, the stuff that comes out of the spacecraft. Okay, and one way to do that is to photolize SO2 with an excimer laser, and that's a very common sort of procedure. People have been doing that for a long time. So then you get these O atoms that are oftentimes excited. And then we can collide them with things that might be coming out of our space vehicles. And we particularly want to look at ethines and propines because they're kind of simple to start with. Yes? And get more complicated from there. All right? So there you go. So we can take oxygen atom and see if we can react them with these things. Okay? And then we want to look at what happens after the collision, what reactions occur, and then what light is emitted as a result of those reactions occurring. And we'll talk about why we want to do that later on a little bit here. Okay? All right, so that's the big overall sort of general experimental method, you know, and chemical ease there, right? And here was the first sort of approach that we tried. We have this reaction chamber over here. We plumb in some SO2 gas. We have an excimer laser over here that shoots that way. And then this thing is infrared spectrophotometer. And all you guys in organic chemistry and lab, you all have infrared spectrophotometers. You've seen them all. This one's a little bit special because not only does it take the infrared spectrum, but it takes that infrared spectrum in what we call a step mode approach, which means it resolves it in time. Okay? So it looks at how that infrared emission decays or grows in as a function of time, in addition to the wavelengths of the infrared radiation. Okay? And that's important when you're talking about stuff happening on space vehicles, right? It doesn't stay the same, it's going to be changes. Okay, so it's kind of a fancied up infrared spectrophotometer, so that's pretty neat. So we did this with this little bench chamber here, and we got some things that looks pretty good. Okay? All right, so here's some sort of data that we get out of something like this. So you get your normal infrared spectrum down here, and if you just took a slice through time, you'd have a normal IR spectrum like you'd see in organic chemistry class, right? With absorptions for CO2 and formaldehyde, and the formal radical over there, CO and stuff like that. But now we also get this time profile as you go back on this dimension going that way. Okay? So I can see how these infrared emissions decay as a function of time. Okay? So big pictures there. So we showed with this little reaction chamber that we could get this kind of data. Right? We could do it. So then it came time to scale up. And boy, did we scale up. We went from this little benchtop thing that was like, foot high to this mother of all reaction chambers. Okay, that comes from vintage Cold War era stuff. Yeah, that chamber that you see behind me is on the second floor. It's almost 3 stories high. Okay, the bottom floor is all pumps, big 30-inch diffusion pumps, if you know anything about that. Roof blower pumps, all kinds of pumps down there to create a vacuum in the straight state chamber, so that you can, simulate, high altitude space type environments, right? The physics type people in here will recognize around there. You see these coils that go around. Those are what they call Helmholtz coils. So you can produce auroras. Can you say that word? Auroras. Hear about those space auroras. So you can do all kinds of stuff with this great big chamber. Yes. Mm-hmm. So we, get the little one. We said we could do it. Now we go to the big one, and we decided, hey, that SO2 thing, that's just too lame, right? We want to go like high throughput stuff here, right? So we built this microwave discharge machine that you kind of see in this picture here. Okay? And what that does is, as oxygen molecule passes through this microwave discharge region, it blows it apart to give us O atoms. Okay? So now we've got a steady stream of oxygen atoms, high abundance. Okay? Really cool stuff. Great big chamber. Yes? Put a pulse valve on the other side of it, so we can pulse in different fuels, things that we come off the spaceship, and see how these two beams collide. So we have a collision, an intersection of two molecular beams in a vacuum. Yes? And then we have all that light focused into our fancied up, time resolved infrared spectrophotometer. Okay? And that was pretty cool. That was neat stuff. Yes, you don't see a chamber like that every day. Yes, you cool it down with liquid nitrogen so you don't get any IR background. Right, we plumb it in directly from the big tank outside that's 3 stories tall. Turn that thing on, boom, boom, boom. You hear the thing cool down. Right, it's like impressive if you're there. Maybe not so much to look at, but when you're there, it's a pretty neat thing. So, that's fun stuff to play with. Okay, when you become a professor in the summer. But bigger toys. Yes? All cool stuff. All right, so what do we look at? We looked at some experiments, and then a question came up with, well, can we develop theories and models to complement, explain, and predict these experimental results that I was showing you earlier? Okay? And so one of the things that I did then is, okay, let's see if we can model these reactions of ethene with oxygen atom, and then go from ethene to propene. A lot of work has been done with ethene, so a lot of stuff in the literature that we can compare our results to. So it's a good place to start with something that you can compare with, make sure that what you do is okay. And then there's not much on the propene, so that would be a good place to go after we've figured out what we're doing with other stuff. That's the plan. All right, so this is what we want to do. Determine the energies of reaction, stability of the intermediates, and the reaction products, and simulate the infrared spectrum of this reaction production to compare with and direct the experimental work. Okay, so ethene. This looks like organic chemistry, huh? Yeah, that's what it is. Yeah, sigh. You know, you become a physical chemist. You think you're done with this organic chemistry, but no. Let me tell you guys, you're never done with organic chemistry. So, you know, get to know an organic chemist and make them your best friend. Right? Meet once today, Dr. Hathaway? No? Sometimes it doesn't work. So, here's some, you know, diagrams here of the reactions that can happen. So you have your, let's see, does this work? There you go. You got your oxygen diradical. See the 2 electrons on there? These are unpaired electrons. This is a triplet state. Okay? Right? So this is not a happy atom. Okay? So he could be very reactive. And you've got that pi bond from the alkene there open to attach. Yes? Mm-hmm. So you got stuff happening here. Okay? Now, the oxygen could add to this carbon, and you get something like this, or it could add across those 2 carbons, and you get what they call an epoxide. Okay? This way we end up with a triplet. Over there we end up with a singlet where all the electrons are paired. Here you can see you still have unpaired electrons, and that's why you still have a triplet, still a diradical. Super rad. Right? Were your parents rad?
Yes.
You did? Okay. All right. And then you ask, well, what can this thing do? Well, it can go on these 3 different ways, right? And do different things. And you follow all the different paths along, and you ask yourself, did I miss any? Right? You got this keto-enol tautomerization that I'm sure Dr. Hathaway teaches you guys about in organic chemistry. Is it organic 1 or organic 2? Organic 2. All right. How many people here have taken organic chemistry 2? All right, 2 people. All right, so you remember the keto-enol tautomerization?
Sure.
Yeah, all right. All right, so anyway, this is, you know, write out all the chemistry out on here, and you see, well, okay, now how do we model this stuff that we just draw out on the envelope, right? So we use this sort of methodology, okay? And the comp chem students will recognize all this stuff. Gunska's smiling already there, okay? You can use things like molecular mechanics or semi-empirical methods, but of course those are not cool as ab initio methods, right? Which are the purest approach, okay? So these are the ab initio methods of computation that we're going to use to try to build a theoretical model of the chemistry that goes on here, okay? All right. All right, so all this stuff is cool stuff. So this is what we're going to do now. We're going to talk about some of the results of what happened here. Let's look at this guy here. We'll focus on this reaction here as an example. So this initial reaction where the oxygen comes in and attacks that double bond and opens it up to make this ketocarbene, as it's called. All right? But before we do that, let's take a break, because this is hard work. Right? So go see the sites around Boston, and I was living in this town of Waltham, and I found out that Waltham was famous for its watches in the old days. Back when watches had to be wound up, and they had gears and stuff like that. But then what happened to watches? Yeah, they all went digital with batteries and stuff like that, and no more do they make watches in Waltham. But they have museums there to talk about the old days when there were watches there, right? So anyway, that's kind of fun. So maybe I'd share that with you in case you're interested. Maybe you're not. All right, let's go back to work then. Here we go. All right, so this is what we got going on here. Now, what we're modeling here, this looks like a hill of energy that you're falling down, right? Here's what we start with, oxygen and this ethene, and we're going to go down this hill of energy until we get to this product. But the hill is really more like a groove, yes, or a channel through the mountains, okay? So up here you have this surface, and we're really going down this sort of groove of the surface as we go down. So don't think in just 1 or 2 dimensions here. Try to think 3-dimensionally. That we're going down this chute, down into the canyon from the mountains, right? Okay. And so this is what we start out with. We calculate all the energies for all these little steps along the way. And what you see, something goes like that until we get to what we call the bottleneck of the kinetics here. Okay? And then we go down the rest of the way. So each of these points along the way, the energies are calculated, the vibrational frequencies are calculated, all that cool stuff is calculated using those methods from the previous slide that you didn't care about. Right? I cared about them. So, anyway, we can talk more about it later. All right. Okay, now let's take a look at this reaction over here. This is your keto-enol tautomerization, right? Yep, that's what Annabelle's interested in. Okay, one of those favorite ones. Okay, so can we model that reaction? And we can. We model all these guys. So let's take a look at that. Okay, so here's the ketone over there. There's what we call the enol, and it goes through that transition state up there. Yes. Okay, and let's see how this works. So there we start out. Okay, it moves around like that. You see the hydrogen starting to move over to the oxygen. This is the highest energy point along what we call the reaction coordinate. And then the hydrogen moves over to the oxygen, okay, and we have the enol form of this. Okay? And so these guys go back and forth between their ketone form and their enol form. Yes? Okay? And that's important to organic chemists because you want to know which one's reacting, the ketone or the enol. Yes? All right, so we do that. Okay? Here's another one. You take the enol and change the enol into what we call an ethyne or an alkyne and lose some water off of it. Okay? We can model that too. So here we go. We're going to start out with this enol, and we're going to end up with the alkyne and water. Okay? So let's see if we can go through that little story. So here's the enol. Okay? Call it enol because it has an alkene there, a double bond, and it has an alcohol. So it makes it an enol. Yes? Mm-hmm. They're going to call it you, huh? All right. So here we go. There it starts to move. Okay? You can see that hydrogen shift over. This is the highest energy point there. Right? And then we go a little bit further. The hydrogen attaches to the OH, okay? And then that other guy straightens out until you have what we call the ethyne. Yes? Or the alkyne. So this is all important for chemistry to figure out all the energies on these paths, right? See, are they energetically available, right? Can you do this? Will it happen, right? This, and all that kind of stuff. All right, so in the end, you build these little diagrams for all this energy stuff, yes? We call it a little energy diagram, and I put little pictures on there to show you these things. And you show paths that you can take from one to another. So you start out with this, you could go to this guy here, you could go over here along path 3 to this thing, which could go by path 5 to those things, and so forth and so on. This up here is what we call the triplet surface, where you have the 2 unpaired electrons. Down here we have what we call the singlet surface, where all your electrons are paired with respect to their spin. And supposedly you're not supposed to be able to cross from one surface to another surface. Yes, because that would mean you had to flip your electrons, which is, not supposed to do that. But you always do what you're not supposed to do. Sometimes you do what you're not supposed to do. So we have to think about that as well, right? Okay, so we model all this out, ethene and oxygen, and then we use for the kinetics to figure out how fast you get from one place to another, this stuff called RRKM theory, okay? Named after all these guys, Rice, Ramsberger, Castle, and Marcus, okay? And again, the idea is you're going through this pass, right? And the shape of this surface is going to determine how fast you can go through it. Okay, if you're with me. Right? And so these are little equations to help us do that. So here's a little hike I took out in Albuquerque this summer, right? Going through a little canyon trail. And here you can see that the canyon is pretty narrow. Yes, it's kind of hard to squeeze through there, right? So can you get a lot of people through that part of the canyon trail? No, you can't. It's really deep, right? But you can't get people through there very quickly. Where here, if you went up this part of the trail, it's pretty broad and wide. And lots of people could go up that part all at one time. Yes? So when we think about the surface that our molecules are bouncing around on, we have to think about the shape of that surface and ask ourselves, well, how well can the molecules pass through that surface? Right? And the shape is determined by the vibrational frequencies. And so that's why we calculate all those vibrational frequencies. So this is what we do, okay? Right? Figure out all this thing on a molecular sort of level, and then, we put all this stuff down on paper. So we calculate the kinetics as a function of the pressure and as a function of the temperature. From 300 to 3,000, you get a nice order of magnitude change, and then pressures from atmospheric pressure down to thousandths of a torr. So we almost go 6 orders of magnitude there. Yes? Okay. And see if the kinetics change as a function of the temperature and the pressure. Okay? And then we try to tell stories about why they would change this way or that way. So we say here, for example, this is that. Where's my little pointer go? There it is. So at 300 Kelvin, 95.3% of our product is hydrogen plus this aldehyde-looking thing there for propene. Okay, right? And stuff like that. So we do these things. Okay. Right? And we calculate these things based on these kinetics for both the singlet and the triplet surface. And then we say to ourselves, okay, the calculations say one thing, the experiments said something else. One of the differences might be because in our calculations we didn't allow for surface crossings, but we know that molecules don't always behave like they're supposed to. And maybe based on this, we can determine what the surface crossing is from the triplet to the singlet by comparing the experimental results to the calculated kinetics. Yeah? So we did. And what we find out is that surface crossing occurs for this guy here. Okay? He crosses over to the singlet surface as this thing, and then the hydrogen moves over, and you get something like that. Yes? Mm-hmm. And so that was kind of a cool thing. That was pretty neat. Okay? We call this inter-system crossing when you go from a triplet surface to a singlet surface. It's forbidden, they say, but sometimes the rules fit a little bit. Yes? Okay. So these are ethene results, and they're good, right? We compared to what people have reported in literature for doing something similar thing. And so we thought, well, we're pretty smart. We can handle this. We've got our system down, right? We've got methods for doing stuff now, right? So time to go on to the next biggest challenge. And what's the next biggest molecule after ethene? Propene. Propene, yeah. So benchmarking is all good. Okay, we go on to propene. But before that, I tend to wonder what you're doing working for a military, right? Looking for defense research. I mean, is this where a Christian college professor should be? Right? Interesting, there was this group on campus led by the chaplain, and he had this little book club. Right? And the book that we read one summer was this book called On Killing. And it was written by a sociologist, okay, talking about the effects of killing people. And he looked at case studies where you've got people who did kill people but were still in scary places, right? And he talked about the people who were killing people in the scary places. Now look at the difference. And it was very interesting that post-traumatic stress and stuff, that it's not so much related to where you were, but what you were doing where you were. Okay? So, for example, if you were the chaplain's assistant who didn't have a gun, but you were running around in the trenches where everybody was dying and the bombs were falling down, yes, you didn't have near the after effects as the guy who was actually killing somebody else. Right? Now, the study here was just to figure out how do you keep your killers more mentally healthy. Yes, that's what the Air Force's goal was, right? But, you know, it made me think about what we are asking people to do when they serve in the military or someplace else. If you kill somebody, you kill a part of yourself. Yes? And you're asking people to do that. Okay? Right? So anyway, interesting sort of stuff to ponder. So I thought, well, man, I need to go reflect on this. So I went out to Walden's Pond, which is out there. Yeah, that's where, you know, people, Thoreau went there to reflect. Maybe I'll find his cabin and sit back and be nice and quiet and I can think about, but no! Are you kidding? Have you ever been there? It's like a tourist trap now. It's just awful. So, if you're in the Boston area and think you're going to see Walden's Pond, you're going to check out what Thoreau was talking about, so don't bother. It's the exact opposite of what Thoreau was talking about. So let's go back to chemistry here. That's, you know, somewhat comforting after seeing that commercial development of what used to be a nice, pristine sort of place, right? Okay, so here's propene chemistry. You can see it gets a little bit more complicated than the ethene chemistry because now you got 3 carbons and there's more pathways that you can take. Oh, bummer. Yes? But hey, that just means more opportunity as well. Right? So let's check this out and do some chemistry here. So here's an example, right? Let's say we go from this epoxide over there to that formaldehyde thing. And can we do the same thing we did before? And we say yes, here we go. Show some pretty pictures here. Okay? That's one nice thing about chemistry, we have pretty pictures, right? This is what we call a 3-2 hydrogen shift. Note that the hydrogen is going from, just a thing. Here's carbon number 3. 1, 2, 3. The hydrogen here is on carbon number 3. He's going to go to where? Carbon number 2. So keep watching here as he moves. Okay? There he goes on. Okay? There he gets to carbon number 2. And after that 3-2 hydrogen shift, the thing falls apart. Okay? And now you got the formaldehyde and the alkene. This, just like organic chemistry stuff. Remember that? Okay, so cool, okay? Here's a 3-1 hydrogen shift. So watch this. So we're going to go from carbon number 3, this hydrogen here, we're going to go all the way over there to carbon number 1. That's why I call it a 3-1 shift. Okay, so here we go. We start moving along here on our surface. Yes? Oh, there the hydrogen starts to move over from carbon 3 to carbon number 1. Okay? And there it goes the rest of the way. When you get over the top of the hill, the thing falls apart. Okay? So you have a 3-1 hydrogen shift. Now we can calculate all these things and predict, you know, the vibrational frequencies all along the path to figure out what the shape is of the mountain that we're going through. And then we put this all in a big table, right? A whole bunch of numbers, right? That's what scientists do, put numbers in tables, right? Along with the methods that we did to get those numbers and all that cool stuff, yes? And then we again try to figure out where the intersystem crossing is. Looks like it's the same sort of place as it was with the ethene. Yes, when we compare the experiments from our cool big reaction chamber, you know, that big blue thing, right, with the calculations that we made. And so we're happy with ourselves. Here's some more pretty pictures of stuff, right? Okay? And then you put all these things. Oh, here's an interesting story. Okay? Look at this path. Everything goes downhill, right? Yes? There's no top to that path down. Yes? But if you take the same structure and you calculate it with a better method, you can see that, hey, the path does go up over this little mountain peak before it goes back down. Okay? And so this is one little interesting story that we got out of this sort of work. Okay? So again, through all in pretty tables and pictures and stuff like that. And then, you know, what do we say? Well, it provides good information with the experiment. Talk about the intersystem crossing of that ketocarbene thing from the triplet to the singlet when the electrons flip. And this can help us resolve or deconvolute experimental spectrum, right? Just stuff like that there. And then you publish it, and you're happy camper there. Okay, so Jim Dodd was the guy I was working with over there back in those days. Okay, he's now moved on to bigger things. I'm still here at Journal. Okay, anyway, I'm in a better place anyhow, right? So conclusions of what I did. Let's talk about what I did, and then we'll talk about other things. So I calculated these energy pathways, right? Whether you guys understood how all that worked, that's what I did, right? These are take-home methods. Okay? For ethene and for propene, and we can probably do this for butene too, I think. This gets more complicated. And this work is portable. You know, I don't have that two-story reaction chamber here at Laterno, but you know, we have computers and software, and we can do this stuff here at Laterno. All right, now, let's talk about why did we do this stuff, right? Because you guys are already bored with what I did. A couple of you are kind of. All right, so why do we do this? Well, what's this? Satellite, okay? And do we have a lot of satellites? Yeah. And do they cost a lot of money? Yes. Yes, we do. And are they defended very well? No. No, they have no defense. Is it easy to knock a satellite out of orbit? Yes. Actually, it's not very hard. I mean, you got $1 billion satellite, you can knock one out with $1 million missile. That's a pretty good return on your investment, right? You know what the magnitude? Well, if you had $1 million missile, right? Okay? So, these things are just up there, right? Billions of dollars. You guys ever use GPS? Yeah, yeah. Knock out the satellite, there goes GPS, right? There goes your cell phone. There goes your international calling, right? Yes? I mean, the whole world could come to an end. Right? So, the question is, how or what do we do out there in space? You know, there's treaties saying you shouldn't weaponize stuff in space, right? But what if one satellite ran into another satellite? Is that a weapon? I mean, you could say it was an accident, right? Yes. But indeed, satellites already have weapons on them. They got big titanium rods that they can shoot down at you and hit the Earth with as much impact as an atomic bomb, almost, right? Yes? So, lots of stuff up there in space, not well protected. And so the idea is, hey, we need to know a little bit what's going on up there. Yes? We call it situational awareness, right? Or threat level adjustments and stuff like that. Yes? Those are buzzwords that they throw out. And so, all this stuff about this infrared spectrum that we're collecting, okay, we can use to determine what these space vehicles are doing. Okay? If the aft thruster comes on versus the forward thruster, and we know which one it is, we can tell what the people are doing to change the orbital path of that particular satellite or space vehicle. Yes? So if we can take the infrared spectrum from these satellites and other space vehicles and calculate what that was from, then we know what that thing is going to do. Does that make sense? Yes. And the first step of defending yourself is understanding what the situation is. Okay? Is this going to be a problem or is it not? You know, you see that scary Laterno student walking down the road, right? Should you go the other way? Well, he doesn't look too scary. I think the threat's kind of low, right? So, there you go. Okay? So this is a big deal, right? Here's the Air Force Research Lab organized in what it calls directorates. Okay? So I've always worked in what's called the Space Vehicle Directorate. Sounds like the Space Force to me. Yes? Right? In fact, you know, the Air Force talks about the Space Corps as sort of a subgroup of the Air Force already. Yes? Okay? Not as a separate division, but as a part of the Air Force. Because you see, there's a lot of this stuff that's integrated with each other, right? There's this directed energy stuff, right? Star Wars type stuff, right? From the Ronald Reagan eras, okay? And a lot of that stuff is for what? Space superiority, okay? Right? And they want to put them in your weaponized space, you put them on a satellite, otherwise you try to shoot them from someplace else, right? And see what you can do. So, it's not like you can separate one of these out from the other ones. They're all kind of connected with each other. And the space assets actually direct the ground-based assets and things like this, right? And a lot of your space assets are linked to ground-based stations that control the space assets, right? So if you defend space assets, you also have to defend the ground-based stations that they're connected to. So all this discussion of, Space Force is complicated, right? Because where does one end and the other one begin? Yes? Now, that doesn't mean that we shouldn't have a Space Force. The idea of a Space Force is sort of motivation to put resources where they're needed. Yes? Right? So if you have a Space Force, that emphasizes that we have these space assets. All right, with me? Yes? You got land, air, and sea. Well, what about space? You don't mention it. Well, there's stuff up there that's important, right? So maybe we should talk about that as well. Right? The question is, if you start the Space Force and you put assets toward it, will those assets be properly distributed? Right? Or do you have to hire a whole new level of administrators to do it, which would be redundant to what you already have with the Air Force, right? At what point is the Space Force big enough that it needs its own sort of administration? And I don't think it's there yet. Okay? Now you got a few tens of thousands of people working in these space assets, and you got hundreds of thousands of people working in other areas of the military. So it's still dwarfed by other things. Now maybe it'll grow if you make a Space Force. I don't know. Anyway, so that's sort of something to think about. Pardon?
Are they trying to put people in space with this Space Force?
What's that?
Are they trying to put people in space?
Well, that you might think might be the inevitable end of these things, right? I mean, it's a whole lot cheaper not to, right? And if you're trying to do the most for your money, you don't put Buck Rogers up there because it costs too much bucks, right? Okay. To get people to support the space program, they put people into space. Yes? Right? I mean, you can learn everything you learned about the moon without sending people there. That would have cost a lot less money. But would people have supported it? No. So when you're talking about that sort of space exploration, people want Buck Rogers. Right? When you're talking about military stuff, you don't need Buck Rogers. It sells itself. Right? Yes? Yeah, so be smarter with your money. All right. Anyway, this last summer, I went to Albuquerque. Okay? So the lab moved. So I went to Albuquerque. It was a whole lot nicer place to live in Boston in many ways. A lot less traffic. Okay? Yeah, not bad. Okay? So I went there. This is Albuquerque out there. Yes? And you can see, the cat card on my desk, right, for security, and the books I study, war, morality, and the military profession. Right? You got to think about these things, right? Yeah. And there's some cool laser stuff going on in the lab. And I'll have to talk to you more about this next semester. But I wanted to introduce you to this young lady. This is Nikki from Florida. She's an undergrad, like you guys are, right? And she was working in the group as an undergrad, a space scholar, we called her, right? And it's a good deal. I really encourage you guys to apply for these Air Force student summer scholarships. Okay? She got to work in the lab with us, doing all kinds of cool stuff. Okay? She got paid for it. Yes? And not only that, she's going to get a secret security clearance. And that is a very valuable thing. Once you get your secret security clearance and you graduate with a science degree, you can get jobs that nobody else can. Yep. Yep. And so, yeah, maybe they pay you thousands of dollars to work there in the summer, but far more valuable out of this is the security clearance. Okay? So if you're interested at all in this sort of stuff, I would check this out because that security clearance is a big advantage over any other REU, research for undergraduate experience that you could get working at some other academic lab or something like that, right? Okay? Interesting, too, this young lady was a chemistry major. Cool, yeah, that's always cool, chemistry stuff. But she was also an anthropology major.
sense.
Yeah. So think, well, chemists don't think about the human condition. No, I think a well-rounded chemist does. Right? And I'm hoping that you guys at LeTourneau are well-rounded scientists and engineers. Yes? And maybe you have a little concern about anthropology and the human condition. Yes? We talk a lot about the human condition in theology classes, but how do we incorporate it into what we're doing in the sciences? Yes? Is war moral? Right? Yeah? Those are good questions to ask, and I still ponder them. Okay? So anyway, Nikki's a nice young lady. Okay? Had all kinds of interesting conversations through the summer as we talked about these things. Okay? All right, now. I've been working for the Air Force for a long time, and I've yet to find this thing, right? You know, Hanscom was an old place, and I scurried through all the basements looking for this thing, thinking I could find it there, right? And then, you know, I moved to Albuquerque, and I thought, well, maybe it's going to be in Albuquerque, right? I think it's in Colorado Springs. I think it's staying there, right? But eventually, before my Air Force research career ends, I want to find that thing, right? Yes? So,
It's a TV show.
no, that's just what they tell you so that you don't know it's real. They hide it in plain sight, you see? So it's there.
Then how come you didn't find it?
It's a real thing. Yeah. All right. Okay. All right. So anyway, that brings me to the end of my talk here. If you have questions on these things, I'm open to those now. So please let me know if you have questions. Any questions on this stuff? Yes, Dr. Hall, or over here. Yes.
On the slides where you showed the molecules changing from different forms, was that a change that was occurring when you did something to it, or were they just going back and forth?
They were following that energy path over the top of the mountain path and then back down to the other side.
What's making
So all those points along the way relate to those peaks of the mountain.
What was the horizontal axis?
Horizontal axis is whatever you want it to do. We call it the reaction coordinate. Okay? Right? So you're going through different motions. It's not just a bond stretch or a rotation. It's a number of different things that are changing at one time. Yes? You can't put one thing on the horizontal axis because there's a whole bunch of variables that are changing at one time. They're rotating, stretching, a whole bunch of things that happen. But, you know, you take, just take ethene, 2 carbons, 4 hydrogens, yes? How many vibrational motions does it have? Chem students. 3n minus 6, right? So 3 times 4 is 12 minus 6. There's 6 vibrational motions here in ethene. Take propene, you get bigger. Take benzene, you get 30 vibrational motions. And all these things could happen at different times. Then you have rotational and torsional things that happen. There's no one thing that you put along the horizontal axis. Just like when you go up and over the mountain, right? You're not just going X or Y or Z. You're going all different directions as you go up and over the mountain. I don't know, that's a long answer to it. Probably misunderstood the question. Other questions that maybe I can answer? If you're interested, or you just want to go away and lunch.
It's, Space Force, is it going to act like one of the military branches?
So that's President Trump's goal is to have this extra branch of the military called the U.S. Space Force.
Are they gonna
Military people think we can wait out any politician they put in. Yes, and if we drag our feet long enough, they'll go away. They think this is a dumb idea right now, maybe in the future, but we'll just...
That's how we got the Air Force in the first place.
Maybe.
Because they were the Army Air Corps, and then they just split them off into another branch.
Yeah. I guess the question is it time for the split, or is it not the time for the split? Right? So, yeah. All right. Well, you know, military are in there for the whole life, these guys, right? 20, 30 years. How long is somebody in political office? 4 years, maybe 8, if they're lucky, right?
Maybe 16.
All right. Well, if you have more questions, I'll be down here. Otherwise, see you next week.
16.
Oh, thank you.